So let's start. September 15th, 2017. Something happened 746 million miles from Earth. A spacecraft was about to die. NASA's Cassini probe had been orbiting Saturn for 13 years. It had traveled farther than any human-made object sent to the ringed planet. It had taken over 400,000 images. It had discovered worlds within worlds. But now its fuel was running out. The mission was ending. Engineers programmed Cassini for one final act, a deliberate dive into Saturn's atmosphere, a controlled death. As the probe descended, it transmitted data until the very last second. Then, silence. But what Cassini saw during those 13 years changed everything we thought we knew. It witnessed phenomena so rare, so bizarre, that scientists are still trying to understand them. 8 discoveries that defied explanation. 8 moments that rewrote the textbooks. This is what Cassini saw on Saturn. The things that should not exist. The first discovery happened early in the mission, October 2006. Cassini's cameras turned towards Saturn's North Pole. Scientists expected to see storms, maybe some cloud formations. What they saw instead made no sense. A perfect hexagon, spinning at the top of the planet. Each side measured 9,000 miles long. That's wider than Earth itself. The shape was impossibly precise. 6 perfectly straight edges, 6 perfect corners, rotating in perfect synchronization. Nothing like this had ever been seen on any planet. Hexagons don't just form naturally in gas giant atmospheres. The winds should have torn it apart. The turbulence should have made it chaotic. But there it was, stable, symmetrical, spinning. Scientists ran models. They tried to recreate it in laboratories. Some succeeded in making small hexagons in spinning fluids. But nothing explained why Saturn's hexagon was so large, or why it had remained stable for decades, or why it existed at all. The Voyager probes had spotted it in the 1980s. Cassini confirmed it was still there 25 years later, the same shape, the same size, the same rotation. Inside the hexagon, storms raged. Massive cyclones churned at hundreds of miles per hour. The center held a vortex 50 times larger than Earth's hurricanes, but the hexagon's edges never wavered. They remained locked in place, as if guided by some invisible geometry. Saturn's hexagon is a mystery, a perfect shape in a chaotic world. It rotates once every 10 hours and 39 minutes. That matches Saturn's internal rotation period exactly. But how does the atmosphere know Saturn's rotation speed? How does it maintain the shape against the turbulence? No one knows. The hexagon became Cassini's first impossible discovery, but it was far from the last. The second discovery came from the rings. Saturn's rings are famous, bands of ice and rock stretching hundreds of thousands of miles. Beautiful, elegant, timeless. Or so everyone thought. Cassini revealed something stranger. The rings were breathing. In 2009, scientists noticed something odd in the data. The rings were changing thickness, expanding, contracting, pulsing, like lungs filling and emptying. The B ring, the brightest and densest ring, showed the most dramatic changes. In some places it thickened by over a mile. In others it flattened to just 30 feet. The changes followed a pattern, a rhythm, as if the rings were alive. Scientists call it ring breathing. It's caused by gravitational interactions with Saturn's moons. The moons pull on the ring particles. The particles respond by bunching up or spreading out. But the scale of the effect shocked everyone. We're talking about billions of tons of ice and rock moving in unison, responding to gravitational whispers from moons millions of miles away. The breathing happens slowly, over weeks, over months. But Cassini watched it happen, frame by frame, image by image. The rings also showed waves, spiral density waves rippling outward from the moon's gravitational pulls. Bending waves creating vertical ripples in the ring plane, like dropping stones in a cosmic pond. But here's the truly weird part. The rings are thin, incredibly thin. In most places, just 30 feet thick. That's the height of a 3-story building. Yet they stretch over 175,000 miles wide. If you shrunk the rings down to the size of a sheet of paper, they'd be 10,000 times thinner than paper. Impossibly delicate, yet they breathe. They flex. They respond to forces light years away. Cassini captured it all. The breathing, the waves, the motion. The rings of Saturn are not static. They're dynamic, living structures, constantly changing, constantly moving, exhaling and inhaling with the gravity of distant moons. The third discovery was even stranger. Hidden in the rings were creatures, not biological creatures, but moonlets, tiny moons embedded in the ring material. Some were just hundreds of feet across. Others stretched for miles. But they did something remarkable. They created propellers. From space, the formations looked like airplane propellers, two bright arcs sweeping through the ring material. Scientists called them propeller moonlets. The moonlets themselves were too small for Cassini to photograph directly, but their gravitational influence was visible. As they orbited, they cleared gaps in the ring particles. The particles piled up on either side, creating bright, curved arms. Thousands of these propellers dotted Saturn's A-ring. Some stayed in the same orbit for years, others migrated slowly inward or outward. One particular propeller became famous. Scientists named it Blériot, after the French aviation pioneer. Blériot was massive. Its disturbance stretched over 250 miles. Cassini tracked Blériot for years, watching it drift through the rings, watching it interact with other moonlets, watching it carve its path through billions of ice particles. The propellers revealed something profound. The rings are not just debris, they're a nursery. Small moons are constantly forming and breaking apart, growing through accretion, shattering through collisions. The rings are dynamic, evolving, changing. What we see today won't be the same in 1,000,000 years, or even 1,000 years. The propeller moonlets are ghosts of planets that never formed, echoes of the solar system's violent birth, frozen in orbit around Saturn. Cassini found hundreds of them, each one a tiny world, each one shaping the rings around it. The fourth discovery happened on December 5, 2010. A storm erupted. Not just any storm, the Great White Spot. It began as a small disturbance in Saturn's northern hemisphere, a bright patch of clouds. Within weeks, it had grown, and grown, and grown. By January 2011, it wrapped completely around the planet, a single storm encircling an entire world. The head of the storm stretched over 7,000 miles wide. Lightning flashed inside the clouds, 10,000 times more powerful than Earth's lightning. Thunder roared through the atmosphere. The storm churned for 7 months, longer than any storm ever recorded on Saturn. It pumped energy into the atmosphere equivalent to 1,000,000,000 watts. It changed Saturn's temperature. It altered wind patterns. It released gases from deep inside the planet that had been trapped for decades. Scientists call these events Great White Spots. They happen roughly once every Saturn year. That's about 30 Earth years. The last one occurred in 1990, the one before that in 1960. Cassini was the first spacecraft to witness one up close. It watched the storm evolve. It tracked the lightning strikes. It measured the energy output. It recorded the atmospheric changes. The storm revealed layers of Saturn's atmosphere that had never been visible. It dredged up ammonia ice from deep below. It exposed the planet's internal chemistry. But why do these storms happen? Why every 30 years? Why do they grow so large? No one fully understands. Something deep in Saturn's atmosphere becomes unstable. Heat builds up. Pressure increases, then it erupts, like a planetary-scale boil bursting. The Great White Spot was Cassini's window into Saturn's violent interior, a glimpse of the forces churning beneath those beautiful clouds. The fifth discovery changed astrobiology forever. It came from Enceladus, a tiny moon just 300 miles wide. Frozen, lifeless, unremarkable, or so everyone thought. On July 14, 2005, Cassini flew past Enceladus for the first time. The images came back. Scientists stared in disbelief. The moon's south pole was spraying water into space. Geysers, massive plumes of ice and vapor erupting from cracks in the surface, shooting hundreds of miles high. The cracks formed a pattern, 4 parallel fractures. Scientists called them tiger stripes. Each stripe was about 80 miles long, and from these stripes, Enceladus was bleeding. Water, organic molecules, salt, everything you'd need for life. Cassini flew through the plumes. Its instruments tasted the spray. It found water vapor. It found ice particles. It found salts like sodium and potassium. It found organic compounds, carbon, nitrogen, oxygen, the building blocks of life. But where was this water coming from? Enceladus is tiny, it should be frozen solid. Instead, it has a global ocean. Beneath 10 miles of ice, liquid water covering the entire moon. Kept warm by tidal heating. Saturn's gravity squeezes and stretches Enceladus as it orbits. The friction generates heat. Enough heat to melt ice. Enough heat to create an ocean that connects to the surface through the tiger stripes. When pressure builds, the ocean erupts. Water shoots into space. Some of it escapes Enceladus entirely. It forms Saturn's E-ring, the faint outermost ring, made entirely of ice from Enceladus. The moon is slowly evaporating, bleeding its ocean into space, creating a ring around Saturn. But here's the profound part. That ocean has everything life needs. Liquid water, check. Energy source, check. Organic molecules, check. Scientists now think Enceladus might harbor microbial life, living in that dark ocean, thriving near hydrothermal vents, like the ones on Earth's ocean floor. Cassini didn't have instruments sensitive enough to detect life directly, but it showed us where to look. Enceladus went from unknown moon to prime target in the search for alien life, all because of Cassini's discovery, the geysers of Enceladus, the ocean beneath the ice, the possibility of life beyond Earth. The sixth discovery came from Titan, Saturn's largest moon, bigger than the planet Mercury, the only moon in the solar system with a thick atmosphere. Cassini deployed a probe to its surface, Huygens, built by the European Space Agency. On January 14, 2005, Huygens separated from Cassini. It descended through Titan's atmosphere, parachuting down for 2.5 hours. Its cameras captured everything, and what they saw was Earth. Not literally, but eerily similar. Titan has clouds, Titan has rain, Titan has rivers, Titan has lakes, Titan has seas. An entire hydrological cycle, just like Earth, but with one crucial difference. It's not water, it's methane, liquid methane. At Titan's surface temperature of -290 degrees Fahrenheit, methane behaves like water. It evaporates from lakes, it forms clouds, it rains down, it carves valleys, it fills basins. Cassini's radar mapped Titan's surface through the thick clouds. It found hundreds of lakes near the North Pole. Most were small, but 3 were enormous. Kraken Mare, Ligeia Mare, Punga Mare. Kraken Mare alone covers more area than the Caspian Sea. It's hundreds of feet deep, filled with liquid methane and ethane. The shores are covered in rounded pebbles, smoothed by wave action. Yes, waves on another world, another. Cassini detected changes in the lake's sizes over time. They grew during Titan's winter. They shrank during summer. Seasonal cycles, just like Earth. Some lakes showed curious features, smooth surfaces in radar images, meaning they were perfectly calm. Others showed rough textures, waves or bubbles disturbing the surface. The rain on Titan is different from Earth. The droplets are larger. They fall more slowly in Titan's low gravity and thick atmosphere. Imagine raindrops the size of grapes, drifting down like snowflakes, soaking the landscape in liquid methane. Huygens landed on Titan's surface. It transmitted data for 90 minutes before its batteries died. It landed on what looked like a dry riverbed, surrounded by rounded rocks, eroded by ancient methane floods. The surface was soft, like wet sand or mud. The probe's weight created a small impression. Huygens was humanity's most distant landing. The first time we touched down on a moon in the outer solar system, it sent back images of an alien Earth, a world that looks like ours, but runs on completely different chemistry. Titan is the only other place in the solar system with stable surface liquids, the only other place with rain, the only other place with weather. It's a laboratory for understanding how complex chemistry works, how organic molecules form, how they interact. Some scientists think Titan might have life, not life like Earth's, but life based on liquid methane instead of water, organisms that breathe hydrogen instead of oxygen, that use acetylene instead of glucose. We don't know if such life exists, But Titan shows it's possible. The seventh discovery was hidden deep inside Saturn, invisible to cameras, but detected by Cassini's instruments. Diamond rain. It sounds like science fiction, but it's real. Saturn's atmosphere is made mostly of hydrogen and helium, but it also contains methane. Lightning storms break apart methane molecules. The carbon atoms fall deeper into the atmosphere. Pressure increases, temperature rises. At about 2,000 miles depth, the conditions are perfect. The carbon atoms compress, they crystallize, they turn into diamonds. Tiny diamonds at first, just a few atoms across, but as they fall deeper, they grow. Accumulating more carbon, getting larger, heavier. By the time they reach 5,000 miles depth, some diamonds are over an inch wide. They fall like hailstones. A diamond storm inside a gas giant. But it gets stranger. At 8,000 miles depth, the pressure becomes so extreme that the diamonds melt. They turn into liquid diamond rain, drops of liquid carbon, falling through an ocean of metallic hydrogen. Eventually, they might reach Saturn's core. If Saturn has a core, we're not sure. But if it does, it could be surrounded by a layer of diamonds. Billions of tons of diamonds, more than all the diamonds on Earth combined. This isn't just speculation. Scientists recreated the conditions in laboratories. They subjected methane to extreme pressures. They measured what happened. Diamonds formed, exactly as predicted. Cassini couldn't see this directly, but it measured Saturn's magnetic field. It detected the atmospheric composition. It collected data on pressure and temperature. All of it pointed to the same conclusion. It's raining diamonds inside Saturn, and not just Saturn, Jupiter too, Uranus, Neptune. All the gas giants likely have diamond rain. It's one of the strangest weather phenomena in the solar system, and Cassini helped confirm it. The eighth and final discovery was Cassini itself, the grand finale. By 2017, Cassini was running out of fuel. NASA faced a choice. They could let the probe drift into deep space, or they could deliberately crash it. They chose the crash. But not just anywhere. Cassini would dive between Saturn and its rings, her gap just 1,500 miles wide. No spacecraft had ever gone there. It was uncharted territory, potentially filled with ring particles. Any collision at Cassini's speed would be catastrophic, but the data would be worth it. On April 26, 2017, Cassini began its final mission, the grand finale. 22 dives between Saturn and its rings. Each orbit brought it closer to the planet. Each pass collected unprecedented data. Cassini measured Saturn's gravitational field with extreme precision. It revealed how mass is distributed inside the planet. It detected the precise boundary between atmosphere and core. If a core exists, Cassini sampled particles from the innermost rings, dust grains older than the solar system, pristine material from the birth of planets. It measured the rings' mass. Turns out they're much younger than Saturn, maybe only 100 million years old, created by the destruction of a moon. Or a captured comet. Cassini photographed Saturn's atmosphere from above the clouds. It revealed circulation patterns never seen before. Vortices at the poles, jet streams racing at 800 miles per hour. The data painted a new picture of Saturn, more complex than anyone imagined, more dynamic, more mysterious. On September 15, 2017, Cassini made its final dive. This time there would be no escape. The spacecraft plunged into Saturn's atmosphere, traveling at 70,000 miles per hour, its thrusters fired, trying to keep the antenna pointed at Earth, trying to send data until the very end. For 91 seconds, Cassini transmitted. Its instruments measured atmospheric composition, temperature, pressure, wind speed. It sent back readings from inside a gas giant, something no probe had ever done before. Then the thrusters couldn't keep up. The atmosphere grew too thick. Cassini tumbled. The signal cut out. Seconds later, the spacecraft disintegrated, vaporized by friction and heat. Its atoms scattered into Saturn's clouds, becoming part of the planet it studied. Cassini was gone, but its legacy remains. 13 years of data, over 400,000 images, 8 incredible discoveries, and countless smaller revelations. It found moons we didn't know existed. It mapped rings in exquisite detail. It revealed weather patterns on multiple worlds. It detected the building blocks of life. It showed us that the outer solar system is not cold and dead. It's active, dynamic, alive with geological processes. The mission cost $3.26 billion. It involved 27 nations, thousands of scientists and engineers, millions of hours of work. But it was worth it, because Cassini changed our understanding of the solar system. It showed us wonders we never imagined. A hexagonal storm that defies physics, rings that breathe like living things, tiny moons carving propeller patterns through ice, planet-wide storms erupting every 30 years, a small moon with geysers spraying the ingredients for life, a moon with lakes and rain made of methane, diamond rain falling inside a gas giant, and a final plunge that sent back data until the last possible moment. 8 incredibly rare things Cassini saw on Saturn, each one reshaping what we know, each one raising new questions, each one reminding us how little we understand about the universe, but also how much we can learn if we dare to explore. The hexagon still spins. Scientists continue studying it, using ground-based telescopes now, watching it change with Saturn's seasons. During southern summer, the hexagon appeared slightly fuzzy, the edges less defined. But as Saturn approached northern summer, it sharpened. The boundaries became crisp again, the shape more perfect. Seasonal changes affect even this massive structure. The hexagon's winds blow at over 200 miles per hour, faster than the most powerful hurricanes on Earth. Yet they maintain that geometric shape. Computer models suggest it's a type of standing wave, created by differences in wind speeds at different latitudes, like the waves that form in flowing rivers. But scaled up to planetary proportions, still the exact mechanism remains unclear. Why hexagon specifically? Why not pentagon or heptagon? The mathematics suggest hexagons are stable in certain fluid dynamic situations, but proving it requires more observation, more modeling, more time. The hexagon is roughly 20,000 miles across. 4 Earths could fit inside it. The vortex at its center is 2,000 miles wide. Winds there reach 300 miles per hour, the fastest planetary winds ever measured. Inside the hexagon, smaller storms churn. Some last for weeks, others dissipate in days. But the hexagon endures. It's been there for at least 40 years. Probably much longer. We just didn't have the technology to see it before Voyager, and we might not have studied it so closely without Cassini. The breathing rings pose their own puzzles. Scientists want to know exactly how old they are. Cassini's final data suggested they're young, perhaps formed when a comet wandered too close to Saturn, torn apart by tidal forces, shattered into billions of fragments. Those fragments spread into rings, colliding, grinding, breaking into smaller pieces. The process continues today. The rings are slowly eroding. Ring material falls into Saturn's atmosphere. Scientists call it ring rain, tons of material every second. At this rate, the rings might disappear in 300 million years. Saturn won't have rings forever. We're lucky to see them now. In cosmic terms, we're living at just the right moment, a moment when Saturn wears its crown. But the rings also create new structures. Gravitational interactions produce features that appear and vanish, spokes, dark radial features that rotate with the rings, then fade away. Cassini watched them come and go. They seem to be caused by electrostatic levitation of dust particles. Saturn's magnetic field lifts them briefly above the ring plane, creating shadows. Then they fall back. The process repeats. The propeller moonlets continue their silent work, carving paths through the rings. Some grow larger by sweeping up material. Others shrink through collisions. The rings are a battlefield. Constant impacts, constant change. Every orbit brings new configurations. Scientists estimate millions of moonlets exist in Saturn's rings, most too small to detect, but all contributing to the ring's structure, all shaping what we see. Some might eventually grow large enough to become true moons, escaping the rings entirely. Others will be destroyed, ground to dust, incorporated into the rings themselves, its evolution in action. On a scale of millions of years, we see just a snapshot, a single frame in a movie billions of years long. The great white spot has faded now, its energy dissipated, its clouds mixed back into Saturn's atmosphere, But it changed the planet. It released gases that hadn't been seen in decades. It altered temperature profiles. It showed scientists what Saturn looks like when disturbed. The next one won't happen until around 2041. Assuming the pattern holds, we'll need new spacecraft to study it, new instruments, new technology. But we'll be ready, because Cassini taught us what to look for. Enceladus continues to spray. The geysers never stop. They're powered by tidal heating that won't cease for millions of years. As long as Enceladus orbits Saturn, it will be squeezed. It will generate heat. It will melt ice. It will erupt. NASA is planning a return mission, a probe designed specifically to sample the plumes, to look for signs of life, to answer the question Cassini raised: is there life in Enceladus's ocean? We might know within the next 20 years. The instruments we need already exist: mass spectrometers capable of detecting amino acids, microscopes that can image cells. If life is there, we can find it. And if we do, everything changes. Life beyond Earth, not on Mars, not on Europa, but on a tiny moon orbiting Saturn. A moon that's spraying its ocean into space, making it easy to sample. No need to drill through miles of ice, just fly through the plume, collect the particles, analyze them. Enceladus is giving us a gift, a window into its hidden ocean, an invitation to explore. Titan waits as well. NASA and ESA are planning a mission called Dragonfly, a nuclear-powered drone. It will fly through Titan's atmosphere, landing at multiple sites, sampling the surface, analyzing the chemistry, looking for the precursors to life. Dragonfly will launch in 2028. It will arrive in 2034. It will explore for at least 2 years, flying hundreds of miles, studying dozens of locations. It will investigate Titan's methane cycle. It will examine the organic molecules. It will search for signs of biological processes. Even if Titan doesn't have life, it's valuable. It shows us what Earth might have looked like before life arose, a world rich in organic chemistry. But missing that crucial spark. Studying Titan teaches us about our own origins, about the chemistry that led to life, about the conditions that make biology possible, and maybe, just maybe, it will surprise us. Maybe life found a way, a different way, a methane-based way. The diamond rain continues, deep inside Saturn, invisible, unreachable, but happening. Right now, carbon atoms are compressing into diamonds, falling through liquid hydrogen, perhaps accumulating in layers, perhaps forming structures we can't imagine. We'll probably never see it directly. Saturn's interior is too hostile. The pressure would crush any probe instantly, but we can study it indirectly, through gravity measurements, through magnetic field analysis, through seismic data if we could detect it. Future missions might drop seismometers into Saturn's atmosphere, listening for vibrations, trying to map the interior, trying to understand what's happening deep below. The diamond rain is just one mystery. Saturn probably has others. Layers we haven't discovered, processes we haven't imagined. The more we learn, the more questions arise. Cassini's grand finale data is still being analyzed. Scientists are still writing papers, still making discoveries. The mission ended in 2017, but the science continues. Some findings take years to fully understand. The data is complex, the implications profound. Every measurement opens new avenues. Every observation raises new questions. The gravity data revealed Saturn's interior structure. The core, if it exists, is diffuse, not a solid lump, but a gradual transition from liquid to gas. The boundary is fuzzy, spread over thousands of miles. This challenges our understanding of planetary formation. We thought gas giants had distinct cores, solid centers left over from their birth. But Saturn suggests something different. Maybe the core dissolved, mixing into the planet's interior, or maybe it never fully formed. The ring particles sampled during the grand finale are ancient, older than Saturn itself, pristine material from the solar nebula, the cloud of gas and dust that formed our solar system. These particles have been locked in the rings, protected from cosmic radiation, preserved for 4.6 billion years. Their time capsules, windows into the past. Studying them reveals the composition of the early solar system, the building blocks of planets, the raw materials of worlds. Some particles contain organic molecules, complex carbon compounds, the same compounds found in comets and in meteorites and on Earth, the chemistry that led to life. Saturn's rings contain it, frozen, waiting. Cassini's photographs are stunning. They've been turned into posters, screensavers, coffee table books. But they're more than pretty pictures. Each one contains scientific data. Color indicates composition. Brightness shows density. Texture reveals particle size. Scientists analyze them pixel by pixel, extracting information, building models, understanding Saturn. The mission also tested new technologies, the ion engines that powered Cassini, the radioisotope generators that provided electricity, the autonomous navigation systems. All of these have been improved, used in newer missions. Cassini paved the way. The Huygens probe used heat shields and parachutes, technologies refined from Viking and Mars missions, but adapted for Titan, tested in Titan's unique atmosphere, proven successful. Now used as templates for future landers, Cassini cost $3.26 billion, spread over 30 years. From conception to completion, that's about $100 million per year, less than the cost of a single military jet, for knowledge that will last forever, for discoveries that reshaped science, for inspiration that touched millions. Was it worth it? Ask the scientists who built it, ask the students who studied its data, ask the public who watched in awe. The answer is yes, 1,000 times yes, because exploration is what defines us. Curiosity is what drives us. Understanding is what elevates us. Cassini embodied all of that. It was our eyes at Saturn, our hands reaching out, our minds seeking answers. For 13 years it showed us wonders, 8 incredible discoveries, and countless smaller revelations. It taught us that Saturn is not just a planet with rings. It's a system, complex, dynamic, evolving, with moons that spray oceans into space, with atmospheres that rain diamonds, with storms that last for months, with shapes that defy explanation. Cassini's mission is over, but its legacy endures, in the data still being analyzed, in the missions it inspired, in the questions it raised. We'll return to Saturn, maybe not for decades, but we'll return, because Cassini showed us why. It showed us the wonders waiting there, the secrets hidden in the rings, the possibilities beneath the ice. 8 incredibly rare things Cassini saw on Saturn, each one a marvel, each one a mystery, each one a call to explore. The hexagon spins, the rings breathe, the moonlets carve their paths, the storms rage, the geysers spray, the lakes shimmer, the diamonds fall, and somewhere in Saturn's clouds, Cassini's atoms drift, part of the planet now, forever. A fitting end for a spacecraft that gave everything, that showed us worlds we never imagined. That reminded us why we explore. Not for profit, not for conquest, but for knowledge, for understanding, for the sheer joy of discovery. That's what Cassini gave us. That's what those 8 discoveries represent. Moments when humanity reached out, touched the cosmos, and brought back wonder. The mission is complete. The spacecraft is gone. But the inspiration remains. In every student who studies the data, in every scientist who builds on the findings, in every person who looks up at Saturn and thinks, what else is out there? What else can we discover? What else awaits? Cassini answered some questions, but it raised many more. That's the nature of exploration. Every answer leads to new questions. Every discovery opens new mysteries. The journey never ends. It just takes us farther, deeper, closer to understanding our place in the universe. 8 incredibly rare things. 8 moments of wonder. 8 reasons to keep exploring. That's Cassini's legacy, and it will endure as long as humans look up and ask why.